After a century of effort, observations spanning the breadth and width of the cosmos, theoretical insights that push humanity's vision of the universe to its utmost limits, we can finally confidently say without a shred of doubt that the universe is infinite. Or not. See, there's a finite limit to what we can ever observe. But there's almost certainly more universe past that. We just can't see it. But we don't know for sure, and we don't know how far back it goes. And we don't know if the universe curves back on itself or it just is. And then there's the whole multiverse thing, which is its own can of worms. It's complicated. Hey, I'm Paul Sutter, a cosmologist. Let's talk about the universe. Let's start out with something that we can say for certain. We live in an expanding universe. Every single day, the universe gets a little bit bigger than it was the day before. But right away, when we say something like, we live in an expanding universe, certain questions start to pop up. And they're far and away the most common kinds of questions that I get asked. If the universe is expanding, then what is it expanding into? And what is it expanding from? And what's the edge of the universe? And where's the center? I'm gonna be honest with you. I dread these kinds of questions, especially when I give public talks. Not because I know what the answer is, but because I know how totally unsatisfying that answer feels. It's like sneaking into your kid's candy bag the night after Halloween and eating half their chocolates. Don't judge me, I know you've done it too. Feels good in the moment, but instantly you have regrets. Here's the answer. The universe has no center and it has no edge. That's it. That's the answer. No more, no less. And that doesn't really feel good because it doesn't make a lot of sense. It's easy to imagine an expanding universe, and there are plenty of analogies out there to help guide our thinking. We can imagine drawing little galaxies on the surface of a balloon and then inflating that balloon. We see the galaxies are getting further apart. We can imagine baking a loaf of bread with raisins in it. Why it's always raisins and not the far more obvious and delicious choice of chocolate chips is an enduring mystery. But we can see how, as the bread rises, the raisins get further apart. Yay, expanding universe. But the balloon has a center, and it has an edge, and the bread has a center, and it has a crust. Where's the edge of the universe? And where's the crust of the cosmos? This is why we can't rely on analogies too much when dealing with many concepts in fundamental physics. In both the subatomic and cosmological realms, we're grappling with structures and concepts in physics that is far and above what our puny human brains can imagine. That's why we have mathematics. Mathematics is a tool that we can use to understand the universe around us, even when we can't envision what's going on. That's right, kids. Imagination is important. But mathematics can be even more powerful. Let's start with the center. Where did the Big Bang start? Right here, and right there, and right over there. And in the galaxy next door, the Big Bang happened everywhere, all at once. The Big Bang was an event that the entire universe participated in. The Big Bang was not an explosion that happened somewhere in space. It was an explosion of space. It was when the expansion of the universe first got started. It's not a place we can point to, it's a time that we can point to. The Big Bang was a singular event that happened in the past of every single object in the universe. If you take any particle, any bit of energy, and trace its path backwards through time, you'll end up at the Big Bang, where that particle, that bit of energy, gets all mushed together with every other particle and bit of energy in a singularity. Think about it. Let's say the Big Bang happened over there, say in the Andromeda Galaxy. Well then, where were we in the Milky Way when that happened? If we traveled back in time 13 and change billion years ago, would we be watching the Big Bang unfold? But aren't we a part of the universe? How can we be a part of the universe and somehow outside of the event that created it? The Big Bang had to happen everywhere because everywhere is by definition part of the universe. You can't have a universe, especially an expanding one, so no matter where you are, your point in space at one time had to participate in the Big Bang. Now, what about the other side of the coin? If the universe is expanding, then what is it expanding into? Where's the crust in our expanding loaf of bread? And what's the oven that we're sitting in? Go ahead, have another piece of your kid's chocolate because this is going to get weird. There is no edge. The universe has no edge. I don't even want to say something like the universe isn't expanding into anything because that still conjures up the wrong mental image. It's too tempting to imagine a wall or a boundary with galaxies and stuff on one side and nothingness on the other, with the universe expanding to fill up that nothingness with somethingness. It's tempting, but it's wrong. Even the vacuum of space is something. There are still points, locations, existence, even if it's empty. There's no outside to the universe because outside implies existence, even an empty one. But the universe is by definition all there is. There is nothing to physical reality except the universe. Walls separate one region from another, but the universe is all the regions simultaneously. If there were an edge, you can imagine working hard enough to get outside that edge. But that's not possible. There is no outside. There is no side. There just is. Us, the universe, all there is. Like I said, it feels a little thrilling at first, but then the stomach aches kick in. Grab a bottle of Tums and prepare to explain to your kids where all their candy went because we're just getting warmed up. I honestly don't have a decent analogy for you to explain how the universe is expanding without a center and without an edge. It just does, whether we can wrap our minds around it or not. But I can give you a way to start thinking about it. If I were to ask you where is the center of the Earth, you would have no problem pointing it out. It's down there, in the middle of everything, where all the molten hot lava is. Yeah, duh. Okay, great. Now let me ask you a slightly different question. Where's the center of the surface of the Earth? Not the whole three-dimensional sphere, just the two-dimensional surface. In other words, give me the latitude and longitude coordinates of the center of the surface. Is it the North Pole, the South Pole, latitude 0, longitude 0? But all those coordinates are arbitrary. We decided where the line of 0 longitude is by pure convention. It's the line that passes through the Greenwich Observatory in England. And we decided that the equator is where the equator is based on where the sun is at noon during the equinoxes. Yes, we have good reasons for those particular definitions, but we could have just as easily picked anything else. I could, if I felt like it, define my current position as the center of the Earth's surface. So could you. So could anybody. We all have a valid claim to being at the center, which is no claim at all. The entire universe is like the surface of the Earth. No center. Now imagine that the Earth is expanding. Cities getting farther apart with time, continents and oceans growing larger. It's easy to imagine blasting off into space and looking down at the globe, seeing the Earth expanding, swelling like a balloon. But that's cheating, and cheating is only allowed with contributions to Patreon. That's patreon.com/pmsutter, where you get to support this show and keep it going. I truly do appreciate all of your contributions. You can also use the link in the episode description below. There is no outside perspective to the universe, otherwise it would just be a part of the universe. There's no additional dimension that we can access to give us that outside orbital view of the expanding cosmos. We're in it, and it is all of it, and that's it. Living in the universe is like living here on the surface of the Earth. We can figure out if the Earth is expanding. It would take longer to travel between points. Images of distant cities would appear to be redshifted and so on. We could confidently say that the Earth is expanding without ever leaving the surface. All we get is an expanding two-dimensional world, and that's it. But just like living on the Earth, there is a limit to what we can see. On our planet, the horizon is defined by the curvature, and oh yes, curvature is going to come back in a big way in just a little bit. We can't see the entire Earth because it curves down and away from our view. The universe has a horizon too. We only get to see a small portion of it. Take away the expansion of the universe for a second. Just assume that the universe exists and that it's static and much less complicated. If it has a finite age, then there's a limit to what we can see. Light only travels so fast, and the universe is only so old. This means there's a bubble containing all the light that has reached us since the beginning of the universe. It's like shining a flashlight in a dark forest. There's an illuminated portion around us, surrounded by the unknown darkness beyond. Now, if the universe wasn't expanding, then the radius of this bubble would simply be the age of the universe multiplied by the speed of light, which comes out to 13.77 billion light years. And in cosmology, we give this radius a special name, the Hubble radius. radius, or the Hubble distance, named after, of course, Edwin Hubble, the guy who discovered the expansion of the universe. I suppose it would be awkward if we named it after James Hubble or Melinda Hubble, people had nothing to do with cosmology whatsoever. Plus, the more distant objects appear to be younger. Light takes time to travel, so by the time the light reaches us, we don't get to see what a distant galaxy is like right now. We only get to see it as it was when the light was released. We don't see the sun right now. We see the sun as it was 8 minutes ago. We see the Andromeda Galaxy as it was 2.5 million years ago. So the innermost portions of our observable bubble are more contemporary, more modern, more in our time. And as we work our way outwards, we see images of the younger and younger universe. The outermost shell of our observable bubble, right at the very limit of what we can see, is an image of the universe just after the Big Bang. So the observable bubble isn't just a limit in space, representing a physical distance. It's also a limit in time. We can't see anything earlier than the Big Bang because there's no such thing as earlier, but that's a different episode. And so the maximum extent that we can see in space is also the deepest that we can see into the past. But like I said, different episode. It's now 2 a.m. We've eaten most of the candy, but we can't help ourselves. I'm not sure why I picked this metaphor, but I'm not giving it up now. An expanding universe complicates this picture just a little bit, because the universe absolutely refuses to be straightforward. Objects are still emitting light, and that light takes time to travel from over there to over here. But in that intervening time, the universe grows larger, with the average distance between galaxies getting bigger. Yes, I know that sometimes galaxies can collide, but we're talking on average at big scales here. So when we see an image of a distant galaxy, and that light has traveled for billions of years to finally end up in our telescope, we don't know how far away that galaxy is right now at the moment we get the light. We have to turn to a cosmological model that incorporates the expansion history of the universe so we know how much the universe has grown in a given amount of time. Our current best model of the universe is called lambda CDM, which involves both dark matter, different episode, and dark energy, different episode. We can discuss the relative merits and weaknesses of lambda CDM, different episode. But for now, let's just take it as a given, as deviations from lambda CDM don't really change this picture much. The maximum distance that we can see, which is the age of the universe, 13.77 billion years, with the cosmos expanding all that time, is about 45 billion light years away. This distance is known as the particle horizon, the cosmological horizon, or the co-moving horizon, depending on how stylish you feel in the moment. That is the extent of our observable bubble, the maximum extent that we can see in this moment today. But wait, isn't 45 larger than 13.77? Doesn't that imply that the universe is expanding faster than light? Yes. Yes, it does. This isn't a big deal. That's because the speed of light limit only applies to local observations. I'll never see a rocket ship blasting by me faster than light. If you think that's some sort of cheat, it's not. It's how special relativity is constructed. Objects at the far edge of the universe can have whatever speeds they want because they're far away, built into how we understand relativity. In fact, we can calculate the current speed of any object, and that's through the redshift. If a galaxy is moving away from us, then its light will get shifted to redder parts of the electromagnetic spectrum. This is how Edwin Hubble discovered the expansion of the universe in the first place. And in an expanding universe, more distant objects recede faster and faster because there's more space between them and us to expand in the time it takes for the light to reach us. And the turnover point, where objects will recede away from us faster than light, is right at the Hubble distance, 13.77 billion light years away. We can still see those galaxies because their light was emitted a long time ago when they were much closer to us. And if we wait long enough, we can still see some galaxies behind them because, once again, those galaxies were also much closer to us. But there's a limit. It's called the cosmological event horizon, which is ever so slightly different from a black hole event horizon. It's about 17 billion light years away. Any light emitted right now past that distance will never reach us. Ever, no matter how long we wait. And an accelerating universe dominated by dark energy makes this even worse. The cosmological event horizon will continue to grow in the future, but eventually it will reach a limit of around 60 billion light years. But that doesn't mean we'll be able to see everything. Light from the most distant galaxies will get redshifted to wavelengths so large that they essentially become invisible, Even a telescope the size of the universe won't be able to pick them up. In about 100 billion years, everything outside of the local group of galaxies will disappear from view forever, which is kind of depressing. And an appropriate feeling as we've eaten almost all of our kids' candy and now face the grim prospects of their faces the next morning. So let's get away from that and get back to Earth. The surface of the Earth is finite. We can measure it. If it was expanding, then its size will grow in time. And once again, good old Earth helps us understand what the universe might be doing beyond our observable horizon. Our best assumption of what goes on beyond the horizon is that there's just more stuff. More stars, more galaxies, more AI-generated cat videos. Just like we assume that beyond our horizon on Earth, there's more Earth. So how big is the universe? Like in total, even beyond what we can see? Well, the truth is we'll likely never know. The observable limit is just that, a limit. It's not just a limit to what we can see. It's a limit to what we can know. There's a total amount of information contained in the universe and a finite amount of information that we could ever hope to receive even in the infinite future. All we can do is guess. It's totally possible that the universe is infinite, that it just goes and goes and goes without end forever. But it's also possible that it's finite. But how can a finite universe still not have an edge? Well, how can the surface of the Earth be finite and yet not have an edge? Yes, it has an edge in the third dimension. We call it outer space, but again, that's cheating. The two-dimensional surface is both finite and borderless, and it accomplishes that through the seemingly paradoxical feat of being curved. We know that the surface of the Earth is curved. We can measure it without our feet ever leaving the ground. In mathematics, we can build a few tools to give us a clue as to the geometry of the Earth. One tool is triangles. On a perfectly flat plane, when you draw a triangle, the interior angles add up to 180 degrees. Thanks, Euclid. But if you were to bust out a giant marker and pick 3 random cities and draw giant lines connecting them, you would end up with a triangle with interior angles greater than 180 degrees. The other is through parallel lines. On a flat plane, parallel lines never intersect, but on curved surfaces, they do. If you and me start at the equator and follow straight lines moving north, we will eventually intersect at the North Pole. Not because we turned, but because the Earth curved underneath us. We can play the same games with the universe. We look at the light from the very early cosmos, from a special event when the universe cooled from a hot, dense plasma to release a flood of radiation. This is known as the cosmic microwave background, or CMB. The physics of that plasma are actually pretty straightforward. We have a decent understanding of plasmas here on the Earth. And we know from our calculations that there should be slight variations in temperature from place to place across the CMB. And wouldn't you know it, there are. Plus, we can calculate how big those splotches ought to be. If the universe is curved, then the path of light should have bent as it traveled all those billions of light years to us. We then compare how big those splotches are to how big we expect them to be. If they're different sizes, then we know the universe is curved. And those temperature variations in the CMB are exactly the size we expect them to be. And that's how we know that the universe is flat. Case closed, the universe is infinite? Not so fast. If we were to attempt to measure the curvature of the Earth from, I don't know, your neighborhood, we wouldn't have much success. If your triangles are too small or your parallel lines are too short, then you won't be able to get a sense of the overall curvature. We are limited in our measurements to our observable bubble, to our horizon. Everything within that horizon seems to be as flat can be. So maybe the universe is curved, but on much larger scales than our tiny little observable patch. I know the tens of billions of light years isn't exactly tiny, but it is compared to how big the universe could be. The universe could be 10 to the 50 times bigger. It's entirely possible that our universe curves back on itself. That would mean you could travel in one direction long enough and eventually reach your starting point, just like on the Earth. But you would have to travel beyond the horizon, which in an expanding universe is impossible. So this is only possible as a theoretical exercise. And you know what's really wild? And I promise this is the last piece of forbidden chocolate. The universe could be flat and still be curved. Check it out. Take a flat piece of paper and draw some triangles and parallel lines on it. Now bend it into a cylinder. Those triangles are still triangles, and those parallel lines are still parallel. This is the difference between geometry and topology. The geometry of the universe appears to be flat, but one or more dimensions could be closed, meaning they wrap around while still maintaining geometric flatness. And it can get weirder. A Mobius strip is just a cylinder with a rotation made before the ends can connect up. A Klein bottle is just a donut with a rotation. A cylinder, a donut, a Mobius strip, and a Klein bottle are all geometrically flat. In 3 dimensions, there are 17 known distinct topologies that are all geometrically flat. My favorite being, of course, Hansch vent space, which involves hexagonal tiling of the same pattern. We've searched for closed topologies. We've looked for intersection points in the cosmic microwave background or galaxies that appear on opposite sides of the sky. As far as we can tell, the universe is both flat and simple, meaning none of the dimensions wrap around on themselves. But again, there's a limit to what we can see, so we may never know for sure. And I even haven't gotten started on the multiverse, where our universe, even beyond the observable limit, is just one bubble amongst a potential infinity of other bubbles, all expanding away from each other and spawning new big bangs in the spaces in between. But I think that's enough candy for tonight. So what do you think? Is there more beyond the horizon of the universe? Do we live in a multiverse? Is the cosmos curved at some vast distance, or is it just more of the same? Let me know what you think in the comments. It's a big universe out there, but we'll take it one step at a time. Thank you for watching.